Now that we talk about an current standard block cipher, present, which is actually a lightweight cryptographic standard, standardized by ISO. Now we can talk about a very old standard, which actually started it all. This is a data encryption standard, and DES is short. So this is a very important algorithm because it actually trained a lot of cryptographers. Nowadays, we are no longer using it because it is not secure due to the short key length, but still it is important because it is used in triple DES algorithm, but also people are still unfortunately using it for cryptographic purposes. So let's see a little bit historical information about this cipher, see its details and see how it is designed and what is its weaknesses and so on. So in 1973, U.S. National Bureau of Standards (NBC) called for a proposal for a block cipher suitable for federal use. So NBC is the previous version of NIST actually. So they needed an encryption algorithm, so they called for proposals. Initially, I think as far as I know, the initial proposals weren't that good. So NBC called for another proposal, and this time IBM submitted a block cipher based on an earlier internal design called Lucifer. So this algorithm was good and people like it, but NSA tweaked the algorithm by changing its S boxes and it became standard. I think NSA also shortened the key length because Lucifer had 128-bit key, but NSA reduced it to 56 bits for DES. Currently, this DES is known as data encryption algorithm, DEA. So we no longer say standard, but an algorithm because it is no longer a standard. This is really important because of the name. A lot of people still think that it is a standard and they keep using it for cryptographic purposes, which they shouldn't. There are even famous websites or corporations, let's say, as in their web pages, when they talk about encryption, they give the example by using DES, which is kind of misleading people because people think that it is safe to use it, but it is not. So once and for all, let's say it again, you cannot use DES for cryptographic purposes. Okay, it became useless after 1990s since its short key is susceptible to brute force attacks. So that is the main problem. Still, one of the most widely implemented cipher in the world. Again, it is used in triple DES, which I will be mentioning in a few minutes. So, what are the early reactions? MBS organized 2 public workshops and received comments from cryptographers, academia, and from industry. Diff and Hellman claimed that a machine can be built for $20 million to perform exhaustive search on 56-bit key. But MBS responded that such a machine would cost over $70 million to build between 1977 and 1990. It would be 256 feet long and draw millions of watts of power. So at that time, it was kind of claimed that it wasn't possible to do brute force attacks on this cipher. Actually, it is not that correct because also it is not easy to predict technology in this way. This kind of calculations, actually, there are many examples where this kind of calculations turn out to be wrong after the technological advances. For instance, after the use of GPUs in scientific computing, many of these kind of calculations turn out to be wrong. So analysis of S boxes showed that they are carefully chosen. This was because NSA tweaked the algorithm. Some speculated that there might be a trapdoor in the algorithm so that an additional piece of information may allow unauthorized decryption. So to this day, we haven't seen any trapdoor, and crypto community never observed such a trapdoor. So we are kind of assuming that there's no such thing. Academics failed to provide successful attacks until 1990. So what happened is as follows. Biham and Shamir provided the first theoretical attack, and they actually introduced a new cryptanalysis technique, and they named it as differential cryptanalysis. They use the name differential because they are introducing a small differences in the plain text blocks. For this reason, they call it differential cryptanalysis. So it is not that much related to calculus. So they provided the first theoretical attack on DES, which requires less time than exhaustive search. However, the attack requires 2 to the 47 chosen plain text to be captured, which is kind of unrealistic in real life. Then Matsui provided the first experimental cryptanalysis of DES by introducing linear cryptanalysis. It also required too much plain text ciphertext pairs to be captured to perform the attack. But for his experiment, Matsui generated the pairs with 40 days of continuous encryption. He was working at Mitsubishi at the time, and as far as I know, he still works there. So he used the PCs available to him at the corporation, and this is how he performed this attack in 1993. Because nowadays, we have very fast computers, we have very fast CPUs, you can perform this experiment today, but he performed it 30 years ago. Coppersmith, one of the designers of DES from IBM, confirmed that NSA tweaked DES to resist differential cryptanalysis. So this was the idea. The initial design of IBM had weak S boxes, and NSA knew the differential cryptanalysis technique, and they realized that they cannot approve this algorithm for federal use, so they tweaked these S boxes and made it strong against differential cryptanalysis. So IBM wanted to check why the NSA made such a change, so they compared their S boxes and the S boxes modified by NSA, and they rediscovered the differential cryptanalysis too. They went to NSA and they said that they knew this technique for a long time, but of course they need to use it to listen to other countries. So they kind of wanted IBM to keep this knowledge as a secret. So nowadays we know that many secrecy agencies in the world knew this kind of techniques. Japanese claim that they knew it even during the Second World War. But of course, the secret source has to keep this information to themselves. This is why Biham was thankful to them in his keynote speech. He received IACR fellowship. He thanked all of these secret services for keeping this knowledge secret so that Biham and Shamir introduced it publicly for the first time. In 1997, in the Differential project, around 78,000 PCs connected by the internet breaks a message encrypted with DES for the first time in public. So since you can use the internet as a distributed computational power, you can perform this kind of experiments, and breaking DES is not that hard even in 1997. And EFFs designed a machine, they called it DES Cracker. This was a special designed machine containing almost 2,000 custom chips, and this device breaks DES key in 56 hours, which is really fast. So in 1999, DES is only allowed in legacy systems. Triple DES will remain as a standard at least until 2030. This is a standard still by NIST until this year, and most probably it will be extended, but we don't know what will happen in 10 years. But the important thing is that DES trained a generation of cryptographers, because by analyzing this cipher, new cryptanalysis techniques were found, and we obtained a lot of insight about block ciphers. So let's recall the definition of DES. DES has the following properties. The block size is 64 bits. Key length is 56 bits. Actually, it is 64 bits, so it is 8 bytes. But the most significant bits of these bytes are not used for the encryption purposes. It is just for error checking. So in practice, the key length is 56 bits. There are 16 rounds, and the type is face-style. So one problem with this kind of implementation of this kind of algorithms is to use whether little ending or big ending notations. So most of the time, instead of defining this in the definitions, we just try to give a picture, and instead of saying least significant or most significant, we try to enumerate them from left to right or right to left. And for the DES, the leftmost bit position of the 64-bit block is denoted as 1, as bit 1. And the rightmost bit position of the 64-bit block is denoted as 64. So this is kind of actually ambiguous, because nowadays we use the, in other ciphers, we choose the rightmost bit as the first bit. But anyway, for this definition, not to confuse it, we refer to the leftmost bit position of the 64-bit block as bit 1. And recall how the face-style ciphers worked. A general definition is as follows. You have the key schedule, and from the key schedule, you use the master key and produce round keys. You divide the plain text into two parts, left and right. And right part actually goes to the, becomes left part in the next round. But that right part also used as an input to the round function, and the output as is XOR to the left part, and it becomes the right part in the next round. So this picture actually taken from Tics for Cryptographers, which is a good website for using many figures, actually latex codes for figures that can be used in crypto. And this picture is from there. So the big picture is as follows. You have the key, and this key is put inside the permutation, and it is rotated, sometimes 1 bit to the left and sometimes 2 bit to the left. And after that, there is another permutation, and the 48 bits round key is produced here. So the the plain text block is initially put inside the initial permutation, and at the end you have a final permutation. And right part is first put into E function, which is expansion. 32-bit becomes 48-bit. Then the 48-bit XOR to the round key. Then we have the rest of the round function, which has actually substitution and linear layers. In the substitution layer, we have S boxes, and at the linear layer, we have the permutation. Then it is XOR to the left 32 bits. So this is actually the big picture. But now we will see all of these parts in detail.